So we're here to do a wellness check on Noctua because they have a liquid cooler. So far, no RGB LEDs to be found. So things are still somewhat under control. They can keep the least RGB bullshit at a trade show award that I've given them twice for at least one more trade show. This is a liquid cooler. We already talked about this, but they have basically some 3D printed and prototype pieces here that are all intended to go into the pump block to reduce some of the most annoying aspect of liquid coolers with pumps, as opposed to thermosiphons, which we'll talk about in a moment as well. This is obviously a Noctua fan, so this is an existing fan that they've reshaped the frame for, and it's optional to mount on top. It projects the air out towards the VRM components. You hit the memory as well. The thermosiphon we're going to cover today also in depth. So this was briefly shown last year. They are now further along in development. It is a two-phase thermosiphon, meaning that it does a phase change, and so in some ways it's comparable to a heat pipe. And over here, there are a bunch of different types of cold plates, ranging from on acid during design process to what ended up in the thermosiphon. And I am here to ask about why. Because I'm sure there's science, I'm positive there's science I don't understand, and this is part of it. So I would like to learn more about that, and Jakob Dellinger from Noctua will be joining us to talk about it. The Antec case, we talked about the case already, but Noctua's got some performance numbers that are pretty interesting. So acoustic directivity, this is actually a really cool test that I'm interested in, where they put this on a turntable, so like Lazy Susan type test, shoot the mic at it and get noise from different angles and measure the impact of the noise on the microphone as the case rotates. And it's kind of cool stuff. I like it. Something that we could do without crazy amounts of extra testing, so maybe I'll add that to Patrick's test suite. This we'll talk about a little bit as well, some thermals. And then over here, there's the 120 mil G2 fan, which also appears shroud top in the Antec Flux Pro, which is the case that we showed earlier, but now it's actually being formally announced. So they have some numbers. We'll go over that. We've got a lot to talk about at Noctua today, and we don't cover mice, but there is one here, and it does have a fan in it. Let's get into it. Before that, this video is brought to you by Lian Li and the O11D Evo RGB case. The O11D Evo RGB is an updated entry to the famed O11 lineup, retaining heavy support for fan mounts, drive mount locations, and flexibility on component mounting, such as two options for the power supply. The O11D Evo RGB's dual chamber approach aims to maximize cable storage on the backside to streamline cable management, coupling this with a unique vertical GPU mount to showcase the most expensive part in most systems. Learn more at the link in the description below. So for the G2 fans, we already talked about the G2 fans when we did the NH-D15 G2 review. This is a 120. Couple things have changed other than the size, obviously, but one of them is that the RPM offset is a little different. So on the NH-D15 G2, when we reviewed that, the RPM offset between the two fans, as a reminder, Noctua intentionally offsets the RPM between the fans by 25, right? Plus minus 25 on the D15 G2. So this one, it's plus minus 50 instead. The stuff I wanted to just briefly go over is some of their first party test data. So if we do anything with this fan, we'll produce our own, but just for what Noctua was saying, so on a 200 watt heat load with a 49 millimeter by 120 radiator, with that 200 watts going into the plate, they have the original, the NF-A12 by 25 at 40.2 degrees delta T over ambient, and then the G2 at 36.7 delta T over ambient. At 3 degrees or plus or minus is really damn good, honestly, for a cooler. There is kind of a range where you'll see more or less, so especially as the heat load comes down in a lot of our testing, you start to see the performance of the higher end stuff matter less. It depends on where it falls. The air cooler here, so this is call it a 1 degree difference between the 200 watt heat load noise normalized on the U12A, and I just want to point out that the scale of 36 to 34.2, this is what NVIDIA's doing to this industry. This is an NVIDIA chart scale is what this is. But anyway, 1 degree, to be fair, on an air cooler is a lot. That's kind of the difference we tend to see top to bottom on some of the same price ones. For this, we're looking at flow. And so it's at 86.4 versus 94.6 meters cubed per hour between the G1 and the G2. So all this is G1, G2. And that'll run us through the fan. But now let's jump over to the liquid cooler. Okay, so for the liquid cooler, I have some basics, but Noctua is working with Acetec. We'll start with that. So they're using the Acetec Gen 8 platform, Gen 8 V2. Acetec has been around a long time. They're one of the big suppliers. So in the old days, they're known for Corsair, NZXT, EVJ. They made basically everyone's stuff. Now it's diversified a bit, so Appletec's gotten really big as a supplier. And the comment, actually, we were talking earlier, so this is Jakob Dellinger from Noctua, and we were talking earlier where Acetec, for as much shit as I've given them over the years, they, in my experience, have had fewer very widespread failures of gunk buildup specifically. So for all the other comments aside, Appletec's had a lot of major issues recently, and this is one of the challenges with liquid coolers, the AIOs, where especially depending on how they flush the radiator and what materials they're using for it, it can become problematic for gunk buildup. So Noctua, I guess, has the unique challenge of trading basically solely on quality, and so you can't have a thing that has a reliability issue. For the actual, I mean, on the engineering side, can we go through the mass damper design and some of the discussion on the acoustics and the profile?
Yes, absolutely. So as you've said, we've taken Acetec's existing NF-A12 platform, because from our perspective, this is just the most mature platform and the gold standard in terms of reliability. What we contributed is the fans, the mounting, and the pump cover that helps to reduce both vibrations and noise. The working principle behind it is twofold. On the soundproofing level, we use a 3-layer acoustic foam. So we have two, they are shown in black here, two open pore soft acoustic foam layers and a dense mass barrier in between. The two soft layers help to target high frequency noise, and the mass barrier in between helps to target lower frequency noise. The second thing that the acoustic foam does is that it isolates the hard plastic shell outer cover from a vibration point of view. So it makes sure that no vibrations can be transmitted to that outer cover. The second thing we do to prevent that vibration transfer is that we have what we call a floating silicon mount, silicon inserts that again make sure that no vibrations can bypass the acoustic foam structure. And that actually is the working principle of a tuned mass damper. So tuned mass damper attaches one or multiple mass nodes to a vibrating structure or object through springs and dampers. And that's exactly what we do here. We have two mass nodes with the dense acoustic barrier and the outer cover shell. And the acoustic foam, the soft acoustic foam, and silicon inserts act as the springs or dampers in our system.
And we should point out too, so this is not actually what they're using. This is just to show the makeup of it. And from what I understand, you're planning to use a sort of a spongy material for at least the soft foam, is that right?
Yes, absolutely. This is just a 3D printed dummy for illustration now. We don't want to give away the exact foam we're using just now. We're targeting a Q1 release date, so we don't want to give the competition a head start here.
Do you have any plans now for specialized changes to the radiator? Is Noctua doing anything to tune the thickness, the fin density, anything like that?
At this stage, for our very first AIOs, we're really taking the existing Acetec NF-A12 platform that includes both the pump and the radiator. For future endeavors, playing with the radiator is definitely something that we will look into.
Okay, and then for the shroud or the pump block top fan, it's an existing 80 mil Noctua fan, I guess. You've shaped the outside. How close to final is this frame?
This is again 3D printed for the show. From a design point of view, I think there's only a little bit of fine tuning left to do, but the basic design with the frame curved outwards to utilize the Coanda effect to draw more air towards the sides, and also the ribs on the cover itself that help to convert rotational energy from the fan's wake flow.
You're talking about these right here?
Yeah. Exactly. They work in the same way as the airflow amplification system that we use with our desk fan, converting the helix structure of the wake flow into straight kinetic energy, just on a, of course, more microscopic level than we can do with that big funnel.
What I mean, realistically, not to get into like actual performance numbers because I know it's too early to have them, but realistically, how much does this type of thing impact the performance ultimately? And if you need to draw on existing fan knowledge to answer, that's fine. But like, if having a ridge structure versus not, is this a situation of, well, we chase every microscopic improvement we can get because they all add up, or is it like one where it's no, this is a big deal?
No. Honestly, frankly speaking, this is micro-level tuning, not more than that. I'm not going to bullshit you into telling you that this is going to make a huge difference. It just doesn't.
So just adding it all up then.
It helps a little bit to tune, but that's it.
Cool. All right. So you have ETA Q1 2026 here. Pricing too early, I guess?
Pricing too early? It's just something that's still up in the air, I would say.
Okay. Anything else you want to go over with this before we move to the Thermosiphon?
I would say we should speak a little bit about the actual performance benefit we're getting from all that tuning work we spent with the cover. I have to stress that the chart we're seeing here is isolated pump acoustic tests. So that's with the pump suspended on rubber bands, and we're measuring pump noise only. And that means that if you have your pump installed in the system, there can be different results because you have vibration pathways through the motherboard. We cannot predict how your motherboard will resonate on your motherboard tray, things like that. So the improvements you see here look great. Don't get me wrong, we're very happy with them, but it's important to caveat that real-world results in fully assembled systems can be different. So with that out of the way, we're seeing an average 5.7 dBA reduction with our pump cover versus a pump without cover. And that's an important thing to mention, because one thing that we found in our testing is that a lot of the covers out there actually increase noise rather than decrease it compared to the naked pump, so to say.
We were talking about screens, right? So the big screens that everyone puts on the liquid coolers now, I was just telling Jakob that an interesting test for us might be if we do a more micro level test looking at, does the screen influence the general acoustics, especially in a case or something where you might have reflections with a huge screen on top of a pump block or something. The impression I'm getting is that a lot of the engineering focus is going on to specifically acoustics, I guess?
Yes, 100%. So the tuned mass damper principle sounds super simple, right? But unless you do the tuning of basically adjusting the mass, the spring stiffness, the dampening coefficients, and the oscillation frequency of all the individual parts, you can end up with making things worse rather than actually getting the noise down, because it will vibrate more than before. So a lot of engineering time went into exactly that tuning procedure to make sure that we really get the noise levels down consistently and across the entire RPM range of the pump.
Okay. Thermosiphon?
Yes, please.
Question mark? Okay. So this is the two-phase Thermosiphon. Last year you guys showed something. I don't remember how close it was to this, but from what I recall, it was not very. This is pretty far along compared to that. Absolutely. First questions are the top level ones. So starting with, let's just do the basics. Is there an ETA? Is there a price target yet? Is there a performance target? And then we'll get into WTF is a Thermosiphon.
Okay, I'll start from the bottom. There is a performance target that remains unchanged from last year, and that is providing the same performance level, noise normalized, of course, as good all-in-one water coolers at the same form factor. Pricing, nope, way too early. ETA, still too early. I can say that we have made very good progress throughout last year. Last year we had a non-working demo on display. Now we have a functional demo that's actually working on a 9800X3D, looping a game. So it's it's doing its work, but it will require more fine-tuning to get the performance to the level we target and to get the performance as consistent as we need it to be.
Okay, and then Thermosiphon. So correct me if I get anything wrong here before I hand it off to you, but my understanding of the principle is some of this can be thought of as at least the two-phase, similar to a heat pipe, in that you have an evaporator, a condenser type of cycle that's going on. And so as it evaporates at whatever the heat source is, turns into a vapor, goes up through, recondenses, comes down as a liquid, and does all of this in a pumpless fashion. There's no mechanical or electrical component to do the pumping of the liquid. And so there's no reliability component from the pump standpoint. Maybe from the liquid, well, definitely from the liquid itself, permeation's maybe a topic. But you're eliminating the pump itself. How else do you want to break down like a thermosiphon at a top level?
Yeah, I mean, in a nutshell, it's a passive heat transfer device that entirely relies on gravity and fluid density changes to circulate the fluid. And a two-phase thermosiphon has a phase change built into that process, just like you described. We're not just heating up a fluid and making it circulate, but we're evaporating a fluid and then condensing it back to make it circulate. And just like you said, the beauty of all this principle is in the simplicity, because you have no moving parts inside. That means all the trouble we're going through with the all-in-one water coolers to bring pump noise down just don't exist, because there is no pump that could possibly make noise, and that also means that there's no pump that could vibrate and no pump that could possibly fail. So the only lifetime limiting factors are indeed permeation or potentially the buildup of non-compressible gases inside the system.
Is the bubbling something that you're going to acoustically target? Is it a feature? Is it it's a water feature that has a calming element to it? Yeah, like, I mean, genuinely, I know this is, I'm sure, extremely quiet. Does it make any noise at all that you would want to try and filter out, or is it just not an issue?
So I literally stuck my ear into this. I got stuck in between the graphics card and the condenser almost, back home in a quiet lab environment, and I think I could hear it a little bit, but this is something you would not be able to hear from outside a closed system for sure. And this is also something that we are quite confident we can still further improve throughout the development process.
The fans are louder anyway, I'm sure, in the rest of the system. So, all right, so let's go through. I don't know where you want to start. The what was it? Boiling crisis? Is that where? Maybe that's a good place.
Yeah, absolutely. So I think we can explain a little bit why we're not at performance target yet. As I've mentioned to you before, we could have gone out here and just shown you that, yay, we reached our performance target by demoing a unit on a heater dummy where we have uniform heat distribution on the heating element. We're actually making the target there, but we still have some trouble on real-world CPUs that have hotspot-centric heat loads. And to explain why this is the case, we should look a little bit at this boiling curve that basically helps to explain the thermodynamics background of all this. Boiling is not just boiling, but there are different phases to it, or boiling regimes to it. So once you start to increase temperature, this graph here plots excess temperature versus heat flux. Excess temperature means the temperature rise above the saturation temperature of the fluid. So in case of water, saturation temperature is 100 degrees Celsius. And once you start rising the temperature of the hot surface above that level, you will first have a phase of natural or free convection where the fluid in liquid form just circulates, mixes, and slowly dissipates heat towards the top, but you don't have any nucleation or bubble formation yet. And then once you go beyond that 5 degree excess temperature threshold, you enter the phase of nucleate boiling. So you will have the first isolated nucleation sites from where bubbles will start rising. And then the more you increase the temperature, the more bubbles you will have rising, the bigger the bubbles will get, and the more they will start to merge, to interact, and the more violent the entire boiling is going to get. I think everyone has seen it when watching a pot of water boiling. And the interesting thing from a thermal engineering point of view is that for any fluid, the heat transfer capabilities are much better in the liquid phase than in the vapor phase. And that means that the more vapor we have inside the pot, the lower the overall heat transfer possibilities or capabilities will get. And that's why from this inflection point onwards, where we start seeing proper jets and columns shooting up rather than just isolated bubbles, we will slowly see the heat flux curve flatten. And then at this point of critical heat flux, or the so-called boiling crisis, we see the curve actually going down sharply. And by sharply, I mean extremely sharply, because this is a logarithmic scaling on the x-axis. And the reason why this is happening is because once you enter the phase of transition boiling, you will have vapor pockets accumulating on the hot surface and effectively insulating the surface from a thermal perspective from the liquid above. And this makes the curve drop all the way down to the so-called Leidenfrost point, at which the film boiling phase starts. And in this phase, you'll actually have a full vapor film covering the surface and shielding it from the liquid above. This phase is also called dry out because at this stage you have no more liquid actually touching the hot surface. Some of you may have seen the phenomenon that when you drop a little bit of water onto a hot plate, like on a stove, you can see it like hovering around, right?
It looks like liquid nitrogen.
Exactly, and that's precisely because of this effect that there's a vapor cushion forming between the hot surface and the droplet of water, and it can take surprisingly long for the droplet of water to dissipate. It's named after German scientist, 18th century scientist Johann Gottlob Leidenfrost.
And what so you were talking about how one of the challenges you guys are running into right now is hotspot specific performance. All of this relates back to that? To the hotspot? Okay.
Because if we look at modern CPUs, we know that they have hotspot-centric heat loads. So for AMD, it's towards the south side of the package, and for at least the 20 and 24 core Intel parts, it's towards the northeast side of the socket. And if we just use the plain, non-treated evaporative surface, that hotspot would translate to a hotspot on the evaporated surface. And this means that we are at a high risk of pushing close towards that point of critical heat flux. And as we've discussed, the boiling curve falls down so sharply from there on that we would have significantly reduced thermal transfer in this area, precisely where we need it the most. And this is the reason why we're still not there performance-wise, and a lot of the engineering time over the last year was spent investigating different approaches of how to battle this problem.
What about microfins? So on a liquid cooler, like a open loop and closed loop, there's already some differences in microfin spacing. Yeah. And a lot of that comes down to what are you using to push the liquid through it, the loop. On an AIO, everyone's generally trying to push the fins as close together as possible without impeding the flow too much. Does that process still apply here with the passive system we're talking about?
Yeah, the fluid dynamic situation is completely different with a system like this, and this is the reason why all those evaporator or cold plate designs that we're showing here look so drastically different to what you use from regular forced convection or pumped liquid coolers. We have to keep in mind that first of all, the fluid circulation rates are much lower, up to 10 times lower in our system compared to a typical pumped system. And secondly, we've already spoken about the issue of vapor pockets forming close to the hot surface. So on the one hand, we have the problem that we don't have the pressure rate and fluid and flow rates to push liquid, let's say, through a jet plate into a fine microfin structure. And secondly, we would have the risk of vapor forming like at the bottom of these microchannels, and fluid never, or liquid fluid never ever reaching all the way down.
So do you end up with the vapor cushion again, but on the microfins?
Yeah, and that's why you can see no microfins here.
The last thing I wanted to go over was some of the Antec stuff. So we talked about the Antec case previously in our own coverage at their office. We've already got a lot of stuff on camera here. I really want to just focus on the acoustic directivity. Okay. So can you help break this down for me? Because I've seen in acoustic chambers, I've seen so-called 3D or 360 microphones where they'll have a literal spiral of mics over a thing. I've seen noise cameras. You guys did a turntable, which is, it achieves similar things to a so-called 3D mic. But what is it your numbers are showing? You're comparing, I guess, the original Antec Flux Pro with its 6 stock fans versus the Noctua one, which is the 2 120 G2s and then the remainder 4 are 140 G2s.
Yeah, so it's a one-to-one fan replacement, I would say, with the 3 140 in the front, 1 in the back, and 2 on the bottom intake. So it's really an apples-to-apples comparison, I would say. Yeah, we did a lot of acoustic directivity testing, so we're not just measuring from a single angle, but actually going in 30-degree steps from the front all the way to the back. And I think the results are quite interesting, especially from a case reviewing perspective, because they show that different configurations perform quite differently depending on the direction you're measuring from. We have 50, 75, and 100% fan speed results on display here. And for 50, for example, you can see that the overall ranking is still very clear cut, which is so much quieter that it doesn't make all that much of a difference. But once you go to 75, you can see that the acoustic improvement when measured from 90-degree angle alone is actually not that much anymore. But measured from the front and from the back, we're still quite a bit ahead. And then 100% fan speed is interesting in the sense that it's actually switched rankings depending on from which angle you're looking at it. So measured from the front, we're still a little bit quieter, but measured from the side, we're a little bit louder. Measured from the back, we're a little bit quieter again with the Noctua edition.
Why does that particular behavior happen, you think? I mean, what kind of causes that?
Yeah, I think we have to go into how much more airflow our fans produce in order to explain that. So we have some isolated fan performance data here as well, a PQ chart where we can see that our fan provides better performance throughout the entire curve, no matter the impedance, but also a free flow noise versus flow plot, where we can see that in free flow our fan is actually a little bit quieter, even at full tilt, and consistently delivers more flow at lower noise levels. Now, why do we see slightly higher noise levels, even when average, in 100% fan speed? The main reason is that we're just driving more flow through the system, and thereby also creating more turbulences inside the system. Okay,
that makes sense. I can't resist, at least pointing this out. So I was going to try and save time a little bit, but you have this interesting convergence here where we're looking at the thermal performance, delta T over ambient against the noise level. Was the top CPU and bottom GPU. So GPU down here, and without even really studying the chart, the first thing that jumps out is that convergence point as the delta T over ambient comes down and as the noise level's up here. So what's going on here?
Yeah, exactly. So we've already seen that our fan provides more airflow throughout the entire RPM range, but when we look at the noise versus temperature results on this part, we can see the converging lines. And the reason for this is that on the right-hand side, we tested a, I would say, regular heat load scenario with a 4090 putting out 550 watt and a 9950X CPU.
450 watts.
What did you say?
You said 550, right?
Oh, sorry, 450 watt.
450.
And 9950X CPU putting out 200 watt. And with that setting, we just had a point of thermal saturation where basically the inlet air temperature for the CPU cooler and for the GPU cooler were so close to ambient that further increasing the airflow just didn't help any further.
Diminishing returns.
Yeah, absolutely.
Yeah. So we'll wrap there for Noctua's booth. As always, there's a lot here, and so we have 2 separate discussions with Jakob that'll be going up after the show. One's about thermosiphons, one is about fans and blade angle, which is not the same. as angle of attack, as I've now learned, and you'll get to learn soon in that video. So, Jakob, thank you for joining me.
My pleasure. Thank you very much for coming.
Absolutely, and we will see you all next time.